Okay, hello everyone. I'm Chen Lu, and I'm going to present this section, which is the implementation of arbiter path, XOR arbiter path, and iPath. So let's see the basic construction of an arbiter path. So it has a switch chain, and and in the end, it has an arbiter that will generate a response for us. So in every stage of the switch chain, it is a switch that will, based on the challenge bit, it will either go parallel or swap the two paths. So let's see how to implement this component. So when we want to implement one switch stage, then usually we will use one local table inside the FPGA, and then we will only use 3 input ports and 2 output ports of the local tables. And for some of the FPGA, the local table may have more input ports or output ports, but we will only use 3 input ports or 2 output ports in this design. And the arbiter is implemented by NAND latch on FPGA. And this arbiter path is, as you all know, this is a delay-based path. So we really need to care about the delay difference on the path between these two paths. So there are some delay difference inside these components that by limiting them into one local table, we can already minimize the delay difference over there. But we still need to care about or pay attention to the delay difference between these two paths, or essentially on the wires. And that's why we want to try our best to maintain the symmetry between these two paths, and then want to minimize the path delay difference in the end. So after this, let's see how to connect them together. So when we implement arbiter paths, we usually have a very poor uniqueness problem. That means that if you use or download the same arbiter path design on an FPGA, it will always generate almost exactly same arbiter path instance, and they will have exactly same behavior. And this also means that if you want to implement XOR arbiter path, then you will have trouble, because if you have even number of XORs, then you will always get 0. And the reason for that is that the process variation in FPGA does not play a big role in creating an arbiter path instance. And what is playing a big role, that's routing delay variation in FPGA. And it's actually out of control of the FPGA user. So as the FPGA user, we cannot control the routing exactly. We can only control the placement of every single local tables, and then let the EDA tool to automatically route it. So for example, let's see that these two figures show that show the exactly paths that is at the same stage of the arbiter path. So here you see the top path is shown by the red lines here, and the bottom path comes from here to here. So it shows that it has a very significant difference between these two paths. So this difference generates or defines the behavior of arbiter path, and this is why the arbiter path is very difficult to implement on FPGA, and then they need to have different behavior. So what's the solution for that? We need to vary the arbiter path design slightly in every instance. So one way to do that is that we can use programmable delay line, but the recent study showed that a bias in the responses of this kind of PDL-based arbiter paths. So we choose a different approach. That is, we vary the placement of switches in different arbiter path instances. And then by placing the switch in one column of an FPGA and vary the selection of local tables in that column, we can construct different arbiter path designs. So how to select these local tables and how to place them? So there are 2 ways. One is pattern placement. So we place the switch based on a predefined pattern. For example, we say a pattern that choose A and C. So you know, for example, the one local table has one slice has 4 local tables, and it has A, B, C, D. So we only use A and C to in one slice to construct the whole switch chain. So it will look like this. So you have AC, 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 and keep going. And every red block represents one slice. So it uses 2 slices. And another way is to place them randomly. So essentially we place the switch in a randomly selected local table in each slice. So it will be something like this. So it can have B, C, D, B local tables in different slices. And then this can also construct a unique arbiter path. So let's compare these two. Of course, after you do this placement trick, you still need to characterize the uniformity, uniqueness, and the reliability of the path instance before you are going to use it. Because sometimes, even you place it differently, they will still generate arbiter path instances that does not have very good uniformity or uniqueness or reliability. So you want to select something that some arbiter path design that has good properties. After that, you can use the path. So there are some pros and cons of these two placement tricks. The pros of pattern placement that the delay between each switch is more equally distributed because we have a very specific pattern over there. So similarly, on the other side, the cons of random placement that some delays may get significantly larger than the other delays. So you will have some very significant turns in your weights. And it can sometimes lead to a successful attack on the path because some weights are dominating the behavior of the path. So we also did some study on our implementation, and then we show that the standard deviation of the weights are different in these two placement tricks. So clearly that the standard deviation for generated in randomly placed arbiter path is much larger than the arbiter paths that's generated by pattern placement. But this also can help us in some cases because it can provide lots of choices of placement, and it can generate a lot more unique arbiter path instances. So this is also sometimes we may need this kind of placements. But because of these cons, so we call that pattern placement good implementation and random placement as bad implementation. So let's see one example of the distribution of the weights of a badly implemented arbiter path. So you can see that some of the weights are really large, like this one and this one. So essentially these weights will dominate the behavior of this path. So this is some attacking results of our FPGA implementation. So we apply the reliability-based attack on the XOR arbiter paths on FPGA, and these are the results. Shows that a reliability-based attack is practical. And this figure shows that we did some CMAS-based machine learning attack on challenge and response pairs of different type of XOR arbiter paths and I paths. And essentially, this confirms the theoretical finding of our paper that this I path has equivalent behavior as this XOR arbiter paths. And we also performed the reliability-based attack on IPath on FPGA. So as we all know that IPath is secure against the reliability-based attack by its design. So we just use 1-1 IPath in the experiment, which is already the weakest IPath. So if we have a 1-1 IPath that is placed randomly, then actually we can attack such an IPAF by reliability attack. So in our experiment, we found that the model of the upper layer arbiter path was discovered, so attacker can just carry on and attack the lower layer arbiter path. But if we implement this every arbiter path properly using pattern placement, then we are not able to attack it by reliability-based attack. And we also open source all the simulation code, attacking code, and the RPG implementation on the GitHub repository. So you are more than welcome to check that.